thank you very much for the opportunity to speak today. This is going to be a bit of a whistle-stop tour through some of the work myself and a lot of colleagues, many of them in this meeting, have been doing on Lake Nautajärvi in southern Finland. We're mainly going to be focusing this talk on some of the XRF analyses we've been using to reconstruct, firstly, Holocene lake circulation dynamics and how that might be impacted by different climatic regimes through the Holocene. And then secondly, some of the more model-based approaches we're using to try and reconstruct paleoclimate, specifically summer precipitation patterns. So firstly, for those of you that don't know, where are we talking about here? This lake in southern Finland, Lake Nautajärvi here, a very, very whistle-stop tour of where we're talking about. So just about 2.5 hours north of Helsinki. But this is a key lake for a number of reasons for Holocene paleoclimate, and this is primarily due to the Varve composition of the lake, which we'll talk about in a bit more detail. So I should just say, the start of this talk is going to be kind of focusing firstly on the context of Lake Nautajärvi, why it is this important archive. So going through the Varve composition, previous research, and then the new composite stratigraphy we obtained from the centre of the lake in 2023. And then secondly, the main body of the talk is going to be focused on some of the research outputs we've been able to put together using this XRF core scanning data. And I'm going to split this into kind of 3 major topics. So the first, as I said, is going to be on the climatic impacts on lake circulation. Secondly, or thirdly here on this bottom section of the slide, this paleoclimatic reconstructions on summer precipitation. And then thirdly, on the final, if you're all still awake by the final sections of this talk, some of the work I've been doing on looking at how we can use some of these proxy-based model reconstructions to look at volcanic forcing as well on our lake system. So that's where we're at. So let's just quickly go through Nautajärvi. Where is it? What's its key parameters, and why is it an important archive of Holocene paleoclimate? So Nautajärvi is, as we've seen, is this lake in southern Finland. It's a dimictic lake that's currently around 20 meters deep. And the key component of this lake is that it's varved pretty continuously for the last around 9.9 thousand years or so. The varves themselves are almost entirely clastic biogenic, and by that I mean there's clastic deposition in the winter, and this largely reflects winter snow cover in the winter, so snow accumulation, and then melt, the rate and the amount of melt in the spring. And then secondly, the second sublaminae is an organic sublaminae, and this is primarily composed, as we'll see in a few slides' time, of organic material. And this largely reflects, firstly, productivity within the water column itself, but also critically for our precipitation reconstructions, allogenic influx from the catchment. So just on the bottom right-hand side here, we can see what these clastic biogenic varves look like. So this is from our most recent coring campaign. And just to kind of summarize that, a lot of work has been done mostly by Antti and colleagues well before myself and Celia et al. Have been involved in this lake, but there's been a lot of work looking at the Varve structure from Nautajärvi. And it largely follows this clastic biogenic structure, a normally graded clastic boundary in the spring, as we've talked about, reflecting winter snow cover, diatom blooms associated with the overturn signals in this dimictic lake circulation, and then organic productivity or organic material predominating through the summer and subsequent winter seasons. So the parameters of this lake mean that there are some key strengths that it has when we're thinking about paleoenvironmental and paleoclimatic reconstructions. The first, as I've already alluded to, it's continuously varved for the last almost 10,000 years. And this means that firstly, the chronology of this lake is very accurate and precise. Secondly, the Varve structure is pretty uniform. I've put pretty for a reason there. We'll talk about that in a second. It's pretty uniform. It follows this clastic biogenic Varve structure throughout the Holocene, and that is critical if we're thinking about the processes that are going on in this lake over time. And then thirdly, as we've seen in the previous slide, the sedimentation processes associated with this clastic biogenic Varve structure are pretty well understood. So therefore, my argument is here that it makes an ideal test site. I sound like a salesman. To try and understand key parameters of, firstly, lake responses to different climatic regimes over time, and that will be the first section of this talk. And then secondly, it provides this idea that the varve structure is pretty uniform, and it continuously is forming varves right through to the present day. This provides an ideal site to construct these proxy-based paleoclimate models throughout the Holocene, and that will be the second phase of this talk. So with all of that in mind, this was what drew us as part of the Celia's decadal project to go and core this lake again in 2023. And here's a nice photo of pretty much almost everyone I think is in this meeting. So Antti, Saya, Amelia here, Ash Abrook, and myself, who were postdocs of Celia's decadal project. So this coring campaign obtained a new 7.25 meter composite stratigraphy from Nautajärvi, which we very creatively termed Now 23. What we've done, we've transferred Antti's existing varve chronology to this new composite sequence using 237, I think it is, marker layers, marker varves, and they're shown here on the right hand side. An outrageously small font size to fit all of these in. But this is provided as this has allowed us to very nicely transfer the chronology, the varve chronology, onto this new composite sequence. And subsequently, as part of this decadal project, we've subsequently used the Nautajärvi the Now 23 sediments for a wide range of proxy-based analyses, and this includes tephrostratigraphy from Alice Castor-Champion, who I think's in the audience, freshwater biodiversity and biomarker studies by Ash, that he's published earlier this year, and also has another paper in preparation. But the main focus of this talk, as I've said, is going to be on the XRF core scanning aspect of the proxy data. So firstly, the XRF core scanning, but secondly, these Bayesian paleoclimatic reconstructions that have been led primarily by Laura Boyle and myself for the core scanning aspect of Nautajärvi. So that's going to be the focus of this talk. So let's dive straight into the XRF core scanning. Why does it give us? Well, why did we do it, and why does it give us new, really important information or insights into past environments at Nautajärvi? The key thing here is that it gives us an ideal multivariate and high resolution data set here, looking at a number of different elements at very high resolution throughout this varve structure. And this has provided critical new insights into the elemental composition of the varves, which hasn't previously been available. And that's going to be the focus of our lake circulation talk. And then secondly, this multivariate aspect of the data set is absolutely ideal for Laura's Bayesian-based quantitative paleoclimatic reconstructions. Finally, is the resolution of these studies also means that we can look at these abrupt climate changes at very, very high resolution. So in theory, subannual seasonal resolutions. And this is extremely powerful, as hopefully I can convince you later. So to dive straight in, let's look firstly at this first kind of results-based section of this talk, is this climatic impacts on boreal lake circulation. And this is based on a paper that was published earlier this year in Science of the Total Environment, where we used the UXRF data from the Now 23 sequence to investigate subtle changes in the lake circulation regime at Nautajärvi. Why, just to kind of quickly go into some rationale, why have we done this? There's a good amount of research now that suggests that future climatic warming scenarios under the IPCC regimes and the CMIP models are going to have a very significant impact on boreal lake systems. This is primarily due to the lengthening of the summer season and this more extreme climatic variability associated with these climatic changes. And these climatic shifts are inevitably going to have a significant impact on lake circulation patterns, and then in turn that's going to impact water quality of these freshwater lakes, and also the ecosystems that live within them and rely upon them. And therefore the argument is that there's a critical need to get a better understanding of the drivers that may cause shifts in circulation patterns. Using the varve chronology and the UXRF data from Nautajärvi, we can target a specific interval, the Holocene thermal maximum, which we know is the last period, at least in the high northerly latitudes, where we see warmer than modern day temperatures. And therefore, the argument is we can use this Holocene thermal maximum, or HTM, as you'll see in the subsequent slides, as a possible analogue for the lake responses to future warming scenarios. I lied to you, just to kind of context, I lied to you when I said that the Varves structure in Nautajärvi is entirely consistent. I just want to point out before we get into the nitty gritty of the XRF data, that there are some subtle features within the mid-Holocene Varves and Nautajärvi. So you might not be able to see it particularly well in this left-hand image, but hopefully you can make out very subtle horizontal bands here of what look like ferrogenic staining. And when we zoom into this is some of Anti's previous work on some SEM imagery, we can see that these intervals of iron staining in the mid-Holocene seem to coincide with this increased precipitation of these iron-rich colloidal particles, we're calling these spherical objects here that are composed primarily of iron and iron oxides. And this suggests that there's potentially some additional complexity in the lake circulation regime associated just within this mid-Holocene window. And therefore, the UXRF data here provides an ideal data set to try and investigate these iron stain bands further. Firstly, to look at what they might be composed of elementally, where they're focused in the Varvier, and then thirdly, what might be driving their formation. So let's jump straight into the XRF results. Here is this graph from this 2025 paper. I'm not going to go into all of it. There's a few complex wiggles on the next few slides. I'm going to try and tease out the key points of these graphs. So on the right-hand side here, we can see CLR transformed elemental data throughout the Nautajärvi 23 sequence. And then we've got our Varve chronology here on the right-hand side in red. And we can see these steady trends of our siliclastic elements, so titanium, potassium, silicon, etc., seem to form a broadly consistent pattern of high values in the early Holocene from around 9,000 to 7,000 years ago, and this coincides with low sulfur values, which we interpret as low organic content. We then see a transition between 7,000 to 5,000 years ago, where our elemental composition of the Nautajärvi Varves becomes much more organic rich. We also see critically a marked increase in our iron and our manganese particles, these redox sensitive elements, during only in the mid-Holocene, this phase 2 section of the now 23 sequence. And then thirdly, after 5,000 years ago to pretty much the present day, we see that transition back to this more simple mode of relatively uniform iron and manganese concentrations, and then variability in our siliclastic and our organic elements. So the now 23 XRF data allows us to divide our Varve sequence into 3 broad phases. Phase 1, the early Holocene of clastic biogenic Varve formation. Phase 3, after 5,000 years ago, classic biogenic Varve formation. But then critically, in this mid-Holocene period, the Holocene thermal maximum, we have this transition to more organic and redox sensitive variability in our elemental data. This can be, I could have condensed that slide quite quickly by just showing you this PCA. So the PCA of our XRF data shown here on the top right condenses that into a quite nice synthesis, really. We have PC1, so this is the plot of PC1 against PC2. PC1 on the x-axis here, which accounts for around 78.8% of our total variance, seems to be strongly controlled by the shifts between detrital, I've said detrital here, but siliclastic sedimentation on the right-hand side, and then to the left-hand side, we have more organic sedimentation. PC2, on the other hand, is most strongly controlled by these redox-sensitive elements, iron, manganese, and sulfur. And it seems to be that when we look back at our graph here, if we look at our orange and our purple plots on this stratigraphic plot, our purple plot is our PC2 values, our orange plot is our PC1 values. We can see this variability is so much more marked in this phase 2 period for PC2, which we interpret as more variability in our hyperlimnetic oxidation status, which is causing variable oxidation rates of our iron and manganese compounds. I'm not going to talk too much more about the clustering, but the clustering supports this analysis. So the PCA is color-coded here into the clusters. Cluster 1 is the one I want you to focus in mostly on here, where we have our highest iron and manganese values associated with our most organic or our least siliclastic dominated elemental compositions. And these are all focused into the Holocene thermal maximum, and very nicely, they coincide with these aforementioned iron-stained bands that we see only in the mid-Holocene. So our interpretation here is that these colloidal or these iron-stained rich particles are being driven principally by shifts in our lake circulation regime. What is going on? Before we get to these bands in particular, I just want to say that this overall pattern from Nautajärvi allows us to reconstruct lake circulation patterns. As we said on the second slide, the current circulation regime is dimictic, circulating primarily in the spring and the autumn. And the type of Varve formation is entirely consistent throughout phase 1 and phase 3 with this manner of circulation. We therefore interpret that during the early and the late Holocene, the lake circulation regime has been almost entirely dimictic. But the Holocene thermal maximum, the HTM, we interpret this decrease in PC1, as we can see on this right-hand side plot, this orange curve here. This decrease in PC1 suggests the most organic rich sediments in the HTM that coincide with this increased variability in our hyperlimnetic oscillation. What we interpret this to mean is that our circulation during the HTM is weakened. We get reduced clastic influx into our lake and an increase in organic sedimentation, which largely reflects higher stratification regimes and more meromictic circulation types. The key thing here is, though, if you look at the plot below this, so plot D on the right-hand side, this is Antti and colleagues' growing degree days plots from Nautajärvi. We can see that this transition to this weakened circulation regime occurs entirely consistently with this period of warmer, longer and drier summers during the Holocene thermal maximum. So we think that this weakened circulation regime is driven primarily by the background climatic regime. But this doesn't explain these iron-banded deposits that we see only in the Holocene thermal maximum as well. What is causing these changes only in this section of our stratigraphy? So we're just focusing on this region now. Let's zoom in. We interpret when you compare this to regional data, it's quite evident that these peaks, as we can see on our top plot here, A on the right-hand side, A is our PCT values. These peaks seem to coincide broadly with phases of enhanced storminess across the high latitudes of the North Atlantic and climatic cooling events associated with grand solar minima, for example, and sea surface temperature reductions and bond events as well. So our interpretation is that although these climatically variable events in the mid-Holocene are nowhere near the largest that we see in the Holocene overall, they have a much more marked impact on our lake circulation regime. And it seems to be that therefore the circulation regime is much more sensitive only under these warmer background climatic regimes. We've maybe been a bit more speculative at the end of this paper to say that this occurs primarily only when growing degree days, that, as we see from Antti's plot, exceed around 1310 degrees C. And this suggests that boreal lakes may actually become more sensitive if these trends that we see from Nautajärvi are more widely applicable, that boreal lakes become more sensitive to climatic variability and stratification changes under these warmer climatic regimes. I'm not going to talk because I think I've spent enough time on this section of the talk, but yeah, that we've schematically, if you'd like to read more, please have a look at the paper where we kind of go into a lot more detail about the processes we think are controlling this sort of variability. So that's kind of using the XRF data in a more kind of traditional format, but we're now going to go into some of the more model-based processes that we can use our UXRF data from Nautajärvi for. We're going to focus firstly on summer precipitation. I'll justify why that will be in a minute. But the first thing to say is that our UXRF data from a statistical sleight of hand, I'll explain this plot in a bit more detail on the right-hand side in a minute, but to say if you can group your elemental compositions through Varve years, you can see there's a clear seasonal signals in some of our URX elements and element ratios. What we can see here is we've grouped these here into our clastic elements, so these titaniums, silicons, potassiums and calciums here. They seem to peak early in the Varve year, associated with our clastic biogenic formation, our clastic laminae formation. And then we see this suite of other element ratios that seem to peak later in the Varve year. What we can see here is aluminium titanium, broadly a proxy for very fine-grained detrital influx. That seems to peak slightly later than our traditional clastic elements. We have our organic silicates, so this is derived from our silicon titanium ratio, and we seem to see two peaks here, which, if we're being speculative, might relate to our overturn periods of diatom blooms associated with overturn. But critically, the ones I want you to pay most attention to are our aforementioned lake circulation proxies, so these manganese and iron molecules, but also our organic influx proxies. So our incoherent-coherent ratio, which is broadly a proxy for the organic carbon content of our lake, and our sulfur content. These both peak in the latter half of the Varve year, associated with the biogenic sublaminae. Hopefully that's made sense. What we've done then is, so because we can pick out these seasonal elemental signals from Nautajärvi, we can then test whether they are sensitive to regional climatic variability. We've picked some of precipitation for a number of reasons, but one of the key ones is that from some of Anti's original work on the Varve laminae thicknesses, he's shown that the organic laminae thickness have got a weak positive correlation to summer precipitation, which suggests there may be some sensitivity to the Nautajärvi biogenic Varve laminae to summer precipitation regimes. So what we've done is we've grouped these non-clastic elements here that seem to peak in the latter half of the Varve year, and we've compared that against a regional ensemble of reanalysis products. So here we've got, I was trying to be very artsy when I made this plot. This is, if you can't key yourself in, here's the United Kingdom. I'm not sure if you can see my mouse, but this green box here covers Scandinavia. The yellow dot here is Nautajärvi, and the red colours here are showing our positive correlation to our ensemble of reanalysis products over the last 100 or so years to total precipitation. Hopefully that makes sense. If it doesn't, the key take-home message here is that we see from our biogenic elemental composition, we have a positive correlation to Scandinavian summer temperatures at Nautajärvi. And this is statistically significant, quite strongly statistically significant. What does this mean? It means that, well, as I've just said, the Varve elemental composition is sensitive to summer precipitation. This is principally, we've been thinking about why this might be. It's either driven by enhanced organic productivity in the water column, but much more likely derived from this increased allogenic influx from the catchment associated with storminess and rainstorms during the summer months. They erode organic material in the catchment soils, peatlands, etc., erode and then inwash them into the lake, where they're finally deposited through the months ahead. This relationship, this strong relationship between the Nautajärvi biogenic component of the elemental Varves and summer precipitation, we use this relationship now to build a proxy model-based comparison, a reconstruction that hopefully can give us a quantitative model of precipitation variability through the Holocene. We've used two key methods to do this. One is this Bayesian-based approach, which Laura Boyle, who's in the audience, has pioneered, which we've called Scooby-Doo. And that's the main focus of this talk. But I've also been playing around with some machine learning approaches using the carrot ensemble in R as well. So here we are. So we've got this positive relationship to some precipitation in our summer Varve. We're now going to try and use that relationship to our reanalysis data, to use that relationship to apply that to our non-instrumental data to reconstruct past precipitation. We're doing that using the Scooby-Doo package, or the Scooby-Doo package, which is a Bayesian modeling approach, which we can use precisely on data sets such as the Nautajärvi Varves to reconstruct quantitative assessments of past climatic regimes. This has a three-stage process. Firstly, we calibrate our modern XRF data to our reanalysis climatic data, in this instance, some precipitation. So a multivariate correlation here, regression. And then we validate that relationship, typically through some cross-validation approaches. So this is an example from Laura's paper. And then thirdly, we can then apply that relationship that we've built in these first two steps to our fossil, our non-instrumentally compared data to produce a modeled reconstruction throughout the Holocene. Because that wasn't enough for me, because this is the sort of person I am, I've also tried to supplement Scooby-Doo with a second line of machine learning approaches, which which is where we've built this kind of model ensemble here. So we use a similar approach here. I'm not going to go through this in too much detail, but just to say that there are two types of modeling approaches we've used to try and quantify our relationship between our elemental composition of our biogenic varves and summer precipitation. And this broadly, as this slide is kind of overemphasizing the points, this follows a three-stage process, as we've just said. Calibration, stage one. Stage two, the reconstruction by applying this to the fossil record. And then stage three, comparing that to other regional paleoclimate reconstructions to try and investigate key drivers. I should say, because we've done this in two approaches, to make it more simplistic here, I've just created a model ensemble stack between our regression models that we've produced using Carrot in R, and our Scooby-Doo models that we've used using Laura's package here. So this model ensemble stack contains around 5 models, 5 or 6 models, I think it is, that apply this approach. So the first stage is that we need to firstly calibrate and validate our models. What does that look like? So I'm going to present entirely this is the results from our model ensemble stack here. So this combination between Scooby-Doo and our machine learning based models to produce this stack. These are the models that we're going to focus on. I haven't shown this, but the results, the individual model results are pretty similar for all simulations, but the results here are the stack. So on the right hand side here, we see our observational Scandinavian summer precipitation values over the last 100 years. This is our individual model performance, and then this red line is our validation. This is our leave one out cross validation of how well this model can predict observational precipitation regimes. It's pretty good. Its R-square value of 0.53 is pretty strong. It's not perfect, so this is good enough to take us to the next stage, I'd argue. But there's still some key take-home messages here. Is that it's not picking up these extreme variables. So particularly around, for example, 1955, we've got very low precipitation regimes, and either side of that, in the early 50s and the early 60s, very high precipitation values that this model doesn't accurately reconstruct. But overall, we've got a pretty good leave one out cross-validation score here, which we can then apply to our fossil data. And just to kind of show that again in this observed precipitation values on the x-axis against our reconstructed values, we see this pretty nice, steadily increasing curve with this R-square value of around 0.53. So using that, we can then apply this relationship to our fossil data, and here is our results. This is our reconstructed summer precipitation variability from Nautajärvi over the Varves sequence, so over the last 9,500 years or so. What we see here is quite a nice pattern. We see the steadily, we see the steadily increasing pattern from around 10,000 years to around 6,000 years, a pretty flat line from around 6,000 years to around 2,000 years, and then a steady increase up to the present day. What we can do then is compare that to our, the TRACE-21 transient paleoclimate model simulation, and we can see a pretty nice comparison. We've got an R value here of around 0.65. We can see particularly after around 8,000 years ago, these models show pretty consistent patterns in regional Scandinavian precipitation over the Holocene. The earlier back we go, it seems to be that the 8.2 event that is very strong in the TRACE-21 KA data is not accurately represented in our precipitation model reconstruction. But I think this is cause for optimism about the performance of this proxy-based model simulation. What we've done, because I thought would be interesting, would be to look at some of the spectral signals. Can we pick out any of the spectral signals in this pattern? And hopefully this is the spectral pattern from our summer precipitation reconstruction. And hopefully you can see some quite clear decadal to multi-centennial cycles in our summer precipitation reconstruction. Typically, these occur around the 150 to 250 mark. But they seem to be critically more prevalent after around 5,000 years ago. So these signals only seem to become statistically significant after 5,000 years ago. And we've had a lot of thought in the Decadal project about what might be controlling these or driving these signals. Well, and this is again, Celia's been very nice to me to let me let my brain work for quite a long time to think about what might be causing these. And I've come up with a hypothesis here that I'd like to share with you. If we go back to our comparison to our reanalysis data, as we did to show that our summer precipitation was statistically significantly correlated, we can also see some interesting spatial correlations with other climatic indices. So the one I want you to bear most attention to on the right-hand side is this top right plot. This is the zonal moisture flux, so the westerly moisture flux in the troposphere here. What we can see here is a very strong positive correlation in the latitudes directly south of Nautajärvi, and this is entirely consistent with the position of the summer storm track. So our argument here is that our biogenic component of the summer valves at Nautajärvi have got some sort of relationship with the summer storm track position. The bottom left hand image is even more interesting to me. This is the geopotential height, so the potential proxy for blocking indices, so high pressure zones in the upper troposphere, and we can see the statistically significant positive correlation typically over Greenland to the west of Nautajärvi, but also over the Ural Mountains. We see this very nice strong positive correlation to our biogenic laminae over the Ural Mountains here. So we've got a very interesting pattern, and finally I should say a negative correlation to some summer sea ice, annual sea ice, apologies, a negative correlation to annual sea ice extents over Greenland and in the Arctic Ocean. So what's going on here? We seem to have some sort of teleconnections between summer precipitation values in Scandinavia and these atmospheric blocking patterns that we see across the Northern Hemisphere. Just to support that, if we then compare, again, I'm maybe going into too much detail here for this talk, but there's some proxy-based reconstructions of these blocking patterns that we see our positive correlations to at Nautajärvi, so over the Ural Mountains and over Greenland. On the right-hand side here, we can see these are the spectral correlations between these, so between our precipitation reconstruction and our Ural blocking frequency and our Greenland blocking frequency, and we can see some statistically significant positive correlations between these patterns. And this, I think, supports the idea that these shifts in the position of the summer storm track are driving in firstly our shifts in our summer precipitation values at Nautajärvi, and these in turn are controlled by the intensity of summer blocking patterns over the high latitudes of the Northern Hemisphere. So these reconstructions are over the last 1,000 or so years, but we see some very intriguing patterns of consistent spectral variability between atmospheric blocking, sea ice extent, and our summer precipitation over southern Scandinavia. What might be causing this? The idea here, I think, is that this is a very ropey figure from, a very useful figure here from Kautz et al. 2021, to give this idea of, in the warm season, these blocking patterns that we see in this red stippled area here divert the position of the summer storm track. And this leads on the Stoss and Lee side of this blocking pattern, very heavy precipitation regimes. And this is exactly what we see over our southern Scandinavian regime of Nautajärvi, as we can see here. So again, here our blocking over Greenland and our blocking over the Ural Mountains, and our heightened precipitation in the center of these two blocking patterns over southern Scandinavia. So just to summarize, hopefully I've been able to convince you here that Nautajärvi, the biogenic component of Nautajärvi, is sensitive to summer precipitation, and our proxy-based reconstructions seem to show consistent variability with our best transient model simulations through the Holocene. It seems to be the initial, I'm tentative to say this, but I think it's quite exciting, that the initial results seem to suggest that this variability in summer precipitation has varied in response to these ocean atmospheric teleconnections, which has led to a shifting position of the summer storm track and blocking patterns over the high latitudes. But I'm not going to spend too much more time here, but we've also been applying this approach to a number of different lakes. So Tifesay and Zabinski to the south of Nautajärvi. And again, this is only a plot with some other proxy-based models. I'm not going to talk about this in too much detail. But over the last 1,000 or so years, we see quite marked differences in our regional precipitation plots. And this therefore gives us some quite interesting questions to answer about, firstly, whether these models are correct, and secondly, what might be driving these patterns. Okay, so a lot of information there. Hopefully I've still got most of you with me. what I'm going to do now for the final couple of slides of this talk is to go one step further, even more speculative here, is to look at how we can use these Scooby-Doo models here in particular to look at things like volcanic forcing. The argument here is that volcanic forcing is well known to affect, so particularly very large eruptions from the tropical latitudes. These very large eruptions are known to have a quite significant impact on Arctic and high latitude climates. But this is principally known because of from instrumental data, but beyond that, typically from tree ring data. And the argument is that these Scooby-Doo models that provide quantitative reconstructions on not just summer precipitation, but also other climatic variables could be used to try and test these ideas of climatic forcing to volcanic eruptions. A lot of information on this slide, but this is just to say I've tested this very briefly in collaboration with some with some people at the Met Office. We've used this bootstrap superposed epoch analysis to try and investigate whether the climate reconstructions from Nautajärvi are sensitive to these large volcanic eruptions. The way we've done this is I've run models. I'm not going to show you the justification for these today, but summer and winter precipitation and temperature regimes using Scooby-Doo, and then I've looked at the sulfuric injections into the stratosphere from Siegel et al. This plot on the right here is showing the major sulfuric injections into the upper stratosphere, which we know are the eruptions that are most likely to impact climate. I've done a lot of work on this, but I'm going to focus mainly here on these large tropical eruptions. So what you see here, this is the final slide, I think, is here are our superposed epoch analysis. Here are our bootstrapping regimes. So 95% and 5% here are our outer limits. And then on the y-axis of each of these plots are our positive or negative correlations. The vertical dotted line is our eruption. So I should say, sorry, these are for the large tropical eruptions, so VSSI over 15, which are very, very big eruptions, of which we've only had, I think, one in the instrumental period. The last 3,000 years, we've had 24. So if we group these 24 and look at the mean climatic response to these, the seasonal climatic response, we can see a pretty consistent summer warming in Nautajärvi in response to these large tropical eruptions. We see a warming in summer, which is the most marked increase, but we also see an increase in summer and winter temperature response as well on the top right-hand side here also. Our precipitation regimes aren't anywhere near as statistically significant, but we also see a pretty prevalent decrease in summer precipitation associated with this warming in the 2 to 3 years after these major large tropical eruptions. So this is quite speculative at this stage, but I just want to key you into why it's quite exciting, is because this follows exactly the pattern that we see of the Tambora eruption in 1815. So this is a figure from Lutabacker and Pfister here on the right-hand side. If we look at this top left-hand plot of this figure, we can see here this famous year without a summer that Tambora caused over Europe, year without a summer causing major crop failures, etc. Much cooler temperatures in Western Europe, but the interesting thing is here that this large tropical eruption caused warming around our southern Scandinavian region. And this is exactly the pattern that we see from our volcanic forcing plot here on the left-hand side. So I think there's still a lot more work that needs to be done on this approach, but I think there's huge potential here to try and develop a better understanding of volcanic forcing to major volcanic eruptions through time. So I think I'll conclude there. This is not a very nice conclusion slide, but hopefully there's been a bit of interest for all of you VARV interested people in this talk. I've hopefully shown that our UXRF data from Nautajärvi provides a really valuable data set, not only for more traditional approaches at looking at in-lake processes over time, but also in constructing the quantified models of seasonal climate variability over time. So thank you very much. I think that's all I've got. I'm more than happy to take any questions.